This is called Faraday's law of induction. According to Faraday's law of induction, an electric force is induced in a circuit that crosses a magnetic field, which means that an electric current is induced in the circuit. When an electric force is induced in a circuit that crosses a magnetic field that is crossed by a rotating magnet, the current is induced according to the direction of rotation of the magnet. For example, consider a magnet rotating clockwise. The magnetic field of the rotating magnet induces electrical induction in the circuit, and this induced electricity flows along the circuit. In this case, the direction of the current is set perpendicular to the axis of rotation of the magnet. If the rotation direction of the magnet is counterclockwise, the direction of the current is also set counterclockwise. In electromagnetic induction, electrons are not ejected perpendicular to their spin direction. This phenomenon is explained by the interaction between electron magnetic moments and magnetic fields, and is a different concept from electromagnetic induction. When you rotate a magnetic field is formed around the rotating magnet. An electric force is induced in a circuit that crosses this magnetic field, and current flows along the circuit. If the speed of rotation of the rotating magnet remains constant, then the size of the current also remains constant. If the rotation speed of a magnet slows down or stops, no electromotive force is induced in the circuit. Therefore, in electromagnetic induction, the rotation state of the magnet and the occurrence state of the current are related to each other. When the magnet moves back and forth in a straight line, a current is induced due to electromagnetic induction. In this case, as the direction of motion of the magnet changes, the direction of the current also changes. That is, as the magnet oscillates, the direction of the current changes at regular intervals. The reason why the direction of the current changes at the point where the magnet oscillates is explained by Faraday's law of electromagnetic induction. According to Faraday's law of electromagnetic induction, when a magnetic field changes, an electromotive force is induced in a circuit, and as a result, a current is induced in the circuit. When the magnet oscillates, an electromotive force is induced in the circuit as the size and direction of the magnetic field change. At this time, since the direction of the electromotive force becomes perpendicular to the direction of magnet motion, the direction of the current changes. Therefore, at the point where the magnet oscillates, the direction of the current changes. Electrons have spin and therefore have magnetic moments. Therefore, when an electron moving in a magnetic field has a spin direction that matches that of the magnetic field, it absorbs more energy from the magnetic field. In reverse, if the spin direction is opposite to the direction of the magnetic field, the electron absorbs less energy and experiences a force pushing it out of the magnetic field. This phenomenon is very important in electromagnetic induction and interaction. When the magnetic field changes, an electromotive force is induced in the circuit by electromagnetic induction. At this time, when current is induced in the circuit, electrons forming the current move along the circuit. Therefore, if the spin direction of electrons moving in a magnetic field is aligned with the direction of the magnetic field, electrons absorb energy more easily from the magnetic field and the induction effect of current decreases. On the other hand, if the spin direction is opposite to the direction of the magnetic field, electrons absorb less energy and the induction effect of current increases. Various electromagnetic field measuring devices have been developed using this principle in electromagnetic induction. Ferromagnetic, diamagnetic and paramagnetic are three classifications that represent the magnetic properties of matter. Ferromagnetic materials react strongly to magnetic fields, and their magnetism does not disappear when the magnetic field disappears. Metals such as iron, nickel and cobalt are examples of ferromagnetic materials. Diamagnetic materials react weakly to magnetic fields, and their magnetism disappears when the magnetic field disappears.